Welcome to Stage 2 Chemistry and this flipped learning video. So far in Topic 1, monitoring the environment, we've completed global warming and climate change and photochemical smog. And we're moving into volumetric analysis, our first mathematical unit of chemistry this year. Our learning intentions are that concentration can be described by using a number of standard conventions. We must calculate concentration, and then we can convert units, including moles per litre, into grams per litre, percentage weight to volume, parts per million, and parts per billion. And we're going to apply some scientific SI prefix conventions to quantities. So some SI units. Scientific information can be presented using different types of symbols and representations, and scientific conventions assist chemists in explaining concepts, solving problems and making predictions. There are components of effective scientific communication, and mathematics is used widely in chemistry as calculations are necessary to explore many important concepts within the chemistry units. A basic understanding of mathematics is required to successfully interpret data obtained from an experiment and within this Stage 2 course. So scientific notation is the first thing we need to know, and it's a way of expressing numbers that are too big or too small to be conveniently written in decimal point form. The digits are written with the decimal point placed after the first digit, followed by a times 10 to the power that places a decimal point where it should be. It shows how many places it's moved with the decimal point. So scientific notation, a power of 10 with a positive exponent such as 10 to the power of 5, the 5 should be higher up, indicates the decimal was moved to the right. And a power of 10 with a negative exponent such as 10 to the negative 5, which should be up here, up the top, indicates the decimal was moved to the left. Can we give this scientific notation activity a go? And I'll review your work answers when we see you next. So this is some SI prefixes that you'll need to know. A great way of remembering is the great mighty king drank chocolate milk Monday nights past. And here's an example of tables that express values of integers and scientific notations for quantities in biosphere. So for example here, volume of fresh water, the integer scientific notation, KL, significant figures of 4. Because significant figures are something that you'll need to get your head around as we move to the end of the year for their final year exam, which takes into account correct scientific notation and also significant figures. Here's some examples of concentration in moles per litre, what the integer looks like, the scientific notation, and also some examples of concentration of atmospheric CO2. So volumetric analysis is quite an important part of Stage 2 chemistry. It's a way of having a quantitative analytical technique that determines the amount and concentrations of unknown reagents. Calculations are applied to fix stoichiometric ratios in chemistry and their chemical reactions that allow us to find unknown quantities. A titration is a laboratory procedure undertaken to determine these concentrations through measured quantities. And titrations are widely used in monitoring concentrations within our environment and also in quality control consumer products, but throughout a lot of different varieties of chemistry. Examples where quantitative analysis may be used could be water quality checks, wine production, administering some medicines, and in these applications, these concentration measures may vary considerably. Because of this, a range of units are applied where we look at a standard convention to allow concentrations to be expressed appropriately and able to understand through a variety of different people, countries, and different areas. So here's some chemical quantities. We're looking at mass, which is little m, volume, V, mass concentration, which is when we're looking at the mass per unit volume, we have Avogadro's constant, Na, which is the number of particles in 1 mole of a substance, which is 6.022 times 10 to the 23. We also have a mole, which is the little n, and this is the mass of a substance containing 1 mole or 6.022 times 10 to the 23 particles in that substance. The other one you need to know is the big M, which is the molar mass. This is a mass of 1 mole of the substance, and it's G mole to the -1. Write the equations for calculating number of moles, molar concentration, and mass concentration, because these are something you'll need to know and remember, because they're not always on our cheat sheets. So write them down. Don't forget that we also have 2 that will be in volumetric analysis. One where we are given the number of moles, and one where we have the mass of the solution, or the mass of the substance. Sorry. Molar mass concentration, and molar concentration. All of these are super important, and they're important for different reasons. This one, which is big M equals little m over little n, or if we rearrange them, it's n big M, or m equals n times m. So these are the 3 arrangements we might see. These equations look at mass moles that are derived from the unit of molar mass. This one here is when we talk about mass concentration. It represents when we get a gram of a solute per litre of solution, so grams per litre. And this here is where we don't have the mass of the solute, but we have the number of the moles of the solute. So additional units we might need to use, and they've been throughout the last 8 years of exams, where we might convert something from grams per litre to percentage weight to volume, parts per million or parts per billion. So you really need to understand this as well, and why it's really important and how to convert. This is the points you need to keep. I would be writing this down, sticking this up in your bathroom, in the back of the toilet door, in your bedroom, but you'll need to know how to convert each of these points. If you've calculated or been given a concentration that has moles per litre, we know it's number of moles divided by litre. To get it into grams per litre, we'd need to times by our molar mass to get to grams per litre. If we go from grams per litre and we're asked to convert back into moles per litre, we're going to divide by the moles. If we want to move from grams per litre, because we've been given the mass, and we know the mass of the solute in 1 litre of volume, we can work out the milligrams per litre into parts per million. Then we could potentially times by another 1,000 to get micrograms per litre in parts per billion. So you can see here, this is milligrams, grams, moles, okay? And then the conversions, how to get there as well into percentage weight to volume. So significant figures, so important, because at the end of the year exam, you could lose some points by not rounding correctly and not using correct significant figures. So every non-zero digit is significant. Zeros appearing between non-zero digits are also significant, and zeros at the end of a measurement occurring after the decimal place are significant. Zeros that act as placeholders at the end of a number, but before the decimal point, or at the front of the number, but after the decimal point, are classed as not significant. Okay, so examples of scientific notation, significant figures as well. And again here, it's a worked example to show you simple conversions and how it might be used in chemistry. You need to know this. So these are kind of the simple conversions, but there might be questions which use a little bit more math. These are the A questions, A+ questions. And here's some examples of when we need to use some complex conversions. So we have sodium monofluorophosphate, Na2PO3F, is common source of fluoride in toothpaste. There are health concerns related to absorption of high levels of fluoride in human beings. This question asks to calculate the percentage composition of F in Na2, PO3, and F. So it's asking how much is the percentage of F when I look at it in total of the whole composition of the chemical. In one brand of toothpaste, the fluoride concentration is this. Calculate the percentage by mass of fluoride in toothpaste. And a 32 kilogram child uses this grams of toothpaste from a 110 tube of toothpaste to brush their teeth. Calculate the concentration of parts per million of fluoride that is consumed by the child. Okay, so here's some examples of how to do that. We have calculating the percentage composition. So think back to last year when we talked about the percentage. We're looking at the total molar mass of the compound. We want to find the molar mass of the element. We would go into the periodic table to find that because F is 19. And if we added 2 lots of sodium, 1 lot of phosphorus, 3 lots of oxygen, and 1 lot of fluorine, all together we would get a molar mass total of 143.95. So here's the other way of showing it as well for A. So I'm hoping by the end concentrations can be described by using a number of standard conventions, understanding that we use moles per litre, grams per litre, percentage weight to volume, parts per million and parts per billion very frequently. And that you know how scientific prefixes are used and given in quantities in chemistry. Please complete your Essentials and SASTA workbook questions.